Dear students, after studying this module, you shall be able to know the atropisomerism in biaryl compounds, know the conditions for atropisomerism in non-bridged biaryl and bridged biaryl compounds. You should also learn to identify axial chirality in biphenyls. You should also be able to find out absolute configuration, that is R and S, according to Kahn, Ingold and Prelog rules, nomenclature for the biaryl compounds. And you should also study some examples relating to atropisomerism to get a better insight into their stereochemistry. Now let us introduce this topic of atropisomerism to you students. Atropisomers, they can be defined as isomers that can be isolated due to prevention or restriction of rotation about a given single bond, usually between two planar moieties. The term atropisomerism comes from the Greek words a for not and tropos, Greek term for turn. If bulky groups on the ortho position of biphenyl or strained ring structural features are there, bulky substituents or strained rings may enhance the barrier to rotation between two distinct conformations to such an extent so as to allow observation of the occurrence of atropisomers. Now, atropisomerism is also called axial chirality, and the chirality is not simply a center or plane but an axis of chirality. As we all know that the phenomenon of axial chirality relies on the rotational stability about a single bond, the important preconditions for this stability will be discussed in this module. Simple biphenyl can easily rotate by carbon-carbon single bond and it is symmetric, so simple biphenyl achiral. Carbon-carbon sigma bond is known as a pivotal bond. So as you can see here, the pivotal bond, which is the carbon-carbon single bond between the two aryl rings. And here is the structure of biphenyl. Biphenyl substituted on ortho position in molecule 1, which is shown here in the figure, which contains a chiral axis along the biphenyl linkage. The biphenyl rings are perpendicular to each other in order to minimize steric clashes between the four ortho substituents, meaning that rotation about biphenyl bond through the pivotal bond is restricted. The interconversion between the two isomers is restricted and is slow, therefore two separate entities are obtained and thus called isomers, and they can be resolved into separate enantiomers. The first chirality due to restricted rotation about a single bond was described by the scientists Christie and Kenner in 1922, and they successfully resolved the enantiomers of 6,6-dinitrobiphenyl 2,2-dicarboxylic acid, which is shown to you here in the figure, and its enantiomers are also shown. Another useful information or definition of atropisomerism was given by Oki, who said that atropisomers can be regarded as physically separable species when they interconvert with a half-life of more than 1000 seconds, that is around 16.7 minutes at a given temperature. The minimum free energy barrier, that is delta G, required to observe atropisomerism varies with the temperature. Atropisomerism is not a phenomenon which is restricted to biphenyls and other many systems from tertiary alkyl tripcycles to binaphthyls exhibiting atropisomerism. A classical example of atropisomeric binaphthyl is the ligand binap, which is represented as structure number 2 in the figure, the development of which earned the scientist Noyori a share of the Nobel Prize in Chemistry in the year 2001. Once the atropisomerism have been separated, binap can be used as a chiral catalyst for asymmetric hydrogenation of carbon-carbon double bonds and carbon double bonded with oxygen. And you can see here the structure of BiNAp. So let us discuss now the conditions of atropisomerism. There are two necessary preconditions for axial chirality and its observation. First is a rotationally stable axis. Second is the presence of a different substituents on both sides of the axis. So, atropisomerisms isomers are recognized as physically separable species at a given temperature, that they have a half-life of at least 1000 seconds or 16.7 minutes. The minimum required free energy barriers at different temperatures is discussed. So, delta G at 200 Kelvin is 61.6 kilojoules per mole, whereas if you increase it by 100 Kelvin, that is at 300 Kelvin, it is 93.5 kilojoules per mole. However, just increasing it by 50 Kelvin, the value of delta G is 109 kilojoules per mole. The configurational stability of axially chiral biaryl compounds is mainly determined by three factors, and these are combined steric demand of the substituents in the proximity of the axis. Second is the existence, the length and the rigidity of the bridges. Third is the atropisomerism mechanism, different from a merely physical rotation about the axis. For example, photochemically or chemically induced processes. Biaryl atropisomers classified into two categories, and this categorization is based upon the basic structure of biaryl atropisomers. One is the bridged biaryls, second is the non-bridged biaryls. Let us now discuss the first category, that is the atropisomerism in non-bridged phenyls. Biphenyl is an aromatic hydrocarbon with a molecular formula of C6H5 whole twice, because it has two aryl rings. They are separated by a double bond, or they are linked by a double bond separated to each other by that much amount of distance. It is notable as a starting material for the production of PCB, that is the polychlorinated biphenyls, which were once widely used as dielectric fluids and heat transfer agents. Biphenyl is also used as an intermediate for the production of organic compounds like emulsifiers, optical brighteners, crop protection agents and plastics. Biphenyl is insoluble in water but soluble in typical organic solvents. The biphenyl molecule consists of two connected phenyl rings, as I already told you. Biphenyl's ortho positions are substituted with two different bulky groups, which makes it chiral and resolvable due to restricted rotation about the pivotal bond, that is the bond which connects the two aryl rings. Now let us consider and talk about the stereochemistry of biphenyls. Biphenyls do not show geometrical isomerism. It shows conformational isomerism, that is the rotation around a single bond is possible in biphenyls, and especially their ortho-substituted derivatives are sterically hindered. For this reason, some substituted biphenyls show atropisomerism, that is the individual C2 symmetric isomers are optically stable. Some derivatives as well as related molecules such as BiNAp find application as ligands in the asymmetric synthesis. In the case of unsubstituted biphenyls, the equilibrium torsional angle is 44.4 degrees and the torsional barriers are quite small, that is 6 kilojoules at 0 degrees and 6.5 kilojoules per mole at 90 degrees. Adding ortho substituents greatly increases the barrier. In the case of 2,2-dimethyl derivative, the barrier is 17.4 kilocalories per mole, that is almost 72.8 kilojoules per mole. The compound which is given below, numbered as 3, can be resolved at room temperature. You can see here, because adding ortho substituents greatly increases the barrier. So what are the conditions for biphenyls to be enantiomeric or resolvable? Just cannot see the ortho group, but what are the basic conditions? So these are: the planes of two aryl groups must be non-planar. This can be done by introducing bulky groups in the ortho position so that the planar conformations are destabilized due to steric repulsion. As you can see here in this figure, that is how non-planarity is achieved, by placing bulky groups in the ortho position. Most of tetrasubstituted biphenyls can be resolved and quite stable to racemization if at least two of the groups are fluorine or methoxy, provided that A, B, C and D, none of them are hydrogen atoms. Third one, the orthosubstituent increases the restricted rotation through pivotal bond, that is providing for you atropisomerism in non-bridged biaryl compounds by their steric repulsion, as already stated. If the van der Waals radiuses of the substituents are more than hydrogen atom rotation through pivotal bond, that will be restricted and the molecule will show atropisomerism. The van der Waals radius has the order of iodine greater than bromine greater than chlorine, then comes nitro, then the carboxylic acid group, then the methoxy, then fluorine and then hydrogen. Mono-ortho substituted biaryl compounds do not form stable atropisomers at room temperature. This type of compounds, like 4 and 5 as in the figure of the compound, show atropisomerism if both the substituents are bulky in nature. In addition to the bulk of the ortho substituents, the nature and position of other substituents in the ring play some important role in the configuration stability of atropisomers. The bulky groups adjacent to the ortho substituents exert a buttressing effect. So the buttressing effect of the sum of the groups are in the order: nitro exhibits greater effect than bromo, then chloro, then methyl group. The rate of racemization is much lower in compound 1, as shown to you in the figure, than the compound 2, which is just next to it. In the compound 1, the bulkier nitro group is adjacent to methoxy, but in case of compound 2, the bulkier group is adjacent to hydrogen. Compound 1 is having more buttressing effect and racemization is slow as compared to compound number 2. If two substituents on ortho positions are similar, but on meta position substituents are different, then these molecules are less common and it is chiral. So you can see here this effect in this figure. In a biaryl compounds, as you can see here in this 7th compound, which is numbered as 7, where 4 ortho hydrogens or the substituents, with the 4 ortho substituents are equal if these are connected pairwise through 2 bridges as the D2 symmetric diether, or they also show the chiral effect, or they also show the chirality. Heteroaromatic system provides chirality even though their ortho substituents are same. In this molecule, which is numbered as 8, both phenyl rings A and B are perpendicular to each other. Now students, the question arises how to write RS nomenclature for the biphenyl compounds. Supposingly you have a compound, let us take an example, 6,6-dibromo biphenyl 2,2-dicarboxylic acid, which is 3-. As you can see here, this compound numbered as 3-. The RS nomenclature can be given by either viewing a molecule from left hand side or right hand side. Now students, let us concentrate on how to write R and S nomenclature for the biphenyls. We will take one example and we will take other examples also, but let us consider the first example. The molecule in consideration is 6,6-dibromo biphenyl 2,2-dicarboxylic acid. The RNS nomenclature can be given by either viewing the molecule from the left hand side or the right hand side. Now let us view the molecule from the left hand side. If your eye level is on the left hand side, that is my left or to your left, if you see the molecule from the left hand side, you can see here that the bold line and if you draw the structure, you will see the bold line, that is the vertical line, that the groups will be given 1 and 2 according to the Kahn, Ingold and Prelog rules. Then the vertical line, and those groups will be numbered as 3 and 4 again according to the CIP or the Kahn, Ingold and Prelog rules. Then we rotate 1, 2 and 3 positions clockwise. So that is R. Now you note that near our eyes will be the bold line, that is the vertical line, which is converted into the Newman projection. You can arrange the molecule into the Newman projection by rotating to the right hand side, then rotating to the left hand side, then reaching this Newman projection. Now what does the CIP rule say? If we consider the carbon at C2 and the carbon at C6 in this example, the extrapolation of C2 will be like this and C6 will be like this. C6 is connected with C and carboxylic acid. CC, CH and Br having higher atomic number than C itself, hence C2 will have preference over C6. If we follow same rule for C2 dash and C6, therefore C2 dash will have higher preference over C6 dash again. Note, in biaryl compounds, if meta is not substituted, then we can decide the preference by ortho substituents using the CIP rules again. Now students, take a view of the molecule from the right hand side. Then you rotate to the left hand side. Then you rotate the molecule once again till you reach the Newman projection. Then again the view which will be near our eyes will be represented by the bold line, which is the horizontal line. Then that is converted into the Newman projection. The bold line, which is now having the groups 1 and 2 according to the CIP rule, then the vertical line having 3 and 4 according to the CIP rule. Then you rotate 1, 2, 3 clockwise, and then you see that in both the cases, viewing like from left hand side or from the right hand side, you will get a R configuration, not a S. So this is the way you can decide by placing the groups 1 and 2 and 3 and 4 appropriately by rotating the molecules. Either you see the molecule from the left hand side or the right hand side, you can decide the appropriate RNS nomenclature for the molecule in consideration. Let us take another example, which is the RNS nomenclature of binol, which is another biphenyl ligand. Now if you view the molecule from the left hand side and then you put it into the Newman projection, it comes like this, where the bold line is the horizontal line and the groups 1 and 2 are on it. Now if you move, then from 1 to 3 we have a anti-clockwise movement. Let us now view the molecule from the right hand side. Again you view the molecule from the right hand side. Now here the bold line is the vertical line, again having the substituents 1 and 2 as compared to 3 and 4. Again according to the CIP rules, you number 1, 2, 3 and 4. Again if you see 1, 2, 3, the direction is anti-clockwise, thus the absolute configuration of binol is S. Now there is another method, which is the Kelsey method for determining RNS descriptors. This type way of nomenclature of writing biphenyls, we should always view the molecule from the bottom side of the axis. That is according to what is shown in the figure here. Now if you put the molecule, see the molecules from the bottom side of the configuration and you put 1, 2, 3 as the according to the CIP rules, the substituents. Now you can see here that the configuration that you get here is again anti-clockwise, which is the S. Now always write bold line as vertical. That is the Kelsey method of determining the absolute configuration. Second is assign priority according to CIP rules, that is always there according to the earlier rules also, according to the Kelsey rules also, on both ortho carbons of the biaryl and near groups to our eyes should be given preference, that is 1 and 2 according to the CIP rules. Now you always have to put the ortho carbon having CIP numbering which belong to the above plane on the top of the vertical line, and rest CIP number is on the bottom of the vertical line. In this example, priority 1 is on the above of the plane, so we should put on the top of the vertical line, that is the bold line, and 2 on the bottom of the line. Write 3 and 4 as it is on the horizontal line, as it is marked on the orthocarbons of the biaryl. CIP 1, 2, 3 denotes rotates in the clockwise rotation, then it will be R. If it is anti-clockwise, then it will be S configuration. So if you see this molecule now, and if you put the bold line as the vertical, and you put 1 and 2 and 3 and 4 according to the CIP rules, then we see the absolute configuration is S. However, in this molecule, the CIP numbering 2 is above the plane on the vertical line, then it should be written on the top of the vertical line and 1 should be on the bottom of the line. So 3 and 4 should be written on the horizontal line as well. Now, bridged biphenyls. Now let us discuss about the bridged biphenyls. In biaryl systems, 2 orthosubstituents are replaced by single bridging atom, that is 5-membered ring is formed. Rotation is restricted at room temperature and disubstituted fluorine, that is molecule number 10, which is planar, does not show optical isomerism. The effect of bridging on the restricted rotation of biaryl system depends on the size of the ring. If the ring size is 6-membered bridge, still considerably facilitates the rotation but to a lesser extent. In benzonaphthoiranones, that is 11-numbered molecule, they existed racemic mixture of their helically distorted enantiomers, that is S and R, the molecules M and P. The restricted rotation increases with steric demand of the orthosubstituent. Orthosubstituents, when R is hydrogen or methoxy, methyl, ethyl, their half-life at room temperature is less than 1 minute. But if R is isopropyl, its half-life is 28 minutes, as shown to you in this figure. The bridging is 7-membered or more than its orthosubstituent if they are bulkier. These types of molecules, they are numbered from 12 to 14, also show atropisomerism. Now let us discuss atropisomerisms, which is shown in molecules other than biphenyls. Some of the molecules which are different than biphenyls also show atropisomerism. These molecules are linked together through a pivotal bond and rotation around the pivotal bond is restricted. The atoms joined through the pivotal bond are usually sp2 hybridized. One or both of the phenyl groups are replaced by other heteroaromatic or aromatic rings. Appropriately substituted molecules like 15 are resolvable into their enantiomers. Second is the 3,3-bipyridyl, numbered as 16-number molecule, can also be resolved as it exists in 2 enantiomeric forms due to atropisomerism. Third, the 2 phenyl rings, that is A and B, are introduced on the para substitution at biphenyls to form a para-terphenyl derivative, and restricted rotation may arise around 2 pivotal bonds. So 2 terminal phenyl rings, that is A and B, are coplanar as well as coaxial. Molecule number 17, as you can see here, is cis, where both bromide on phenyl ring A and ring B are on the same side. The molecule is C2 symmetric, as you can observe, and also resolvable, and chiral axis is passing through ring A and middle ring of the biaryl, and another chiral axis is passing through ring and middle ring of biphenyl. The cis molecule has 2 chiral axes, so it will have enantiomers as well as diastereomers. So diastereomers, students, are the molecules which are not linked as mirror images. If molecule B is trans, then it will possess the inversion center also and Ci point group, and the compound will be meso, that is equal amount of plus and minus enantiomers. Same like 2 chiral centers in tartaric acid, which combine to give you a meso structure, which finally makes the molecule achiral. If one of the planar ring is replaced by an acyclic grouping, that is substituted alkene, which is 2-dimensional, this type of molecules, that is represented by 19, may give atropisomerism if sufficient steric hindrance is created around the pivotal bond, as shown in the figure. We have learned that atropisomerism is due to restricted rotation around sp2 single bond. The sp3 single bond is restricted through various extent, but the energy barrier is too low, so such type of molecules cannot be isolated. In the tryptosine type molecules, however, the barrier to rotation around 9 substituted bond may be quite high, and these atropisomerisms, the atropisomers, that is 20 and 20 dash, as you can see here, can be isolated easily at room temperature. Now you can see here these molecules 20 and 20 dash, and they can be separated at room temperature. Now, after having discussed about what atropisomerism is, what atropisomers are, and what are the bridged and the non-bridged biaryl compounds, and taking various examples for the nomenclature and the learning about the assignment of the R and S, the absolute configuration in biaryls, I want to summarize this module, students. In this module, we have discussed that atropisomerism in non-bridged and bridged aryl compounds due to restricted rotation through a pivotal bond is arised. Biaryl compounds with appropriate different orthosubstituents on each aryl ring will be there, and so the atropisomerism takes place. The bulkier groups on ortho position of the biaryl ring restrict the rotation through CC bond, gives 2 enantiomers which are resolvable even at room temperature. In bridged biaryl compounds, these compound affects the bridging on the restricted rotation of biaryl system, and it depends on the ring size also. Some of the molecules which are different than biphenyl also show the atropisomerism. The sp3 single bond is restricted through various extents, and tryptosine type molecules, the barrier to rotation around that bond may be quite high. So these can exist as atropisomers and can even be isolated at room temperatures. So students, I hope you found the topic of atropisomerism very fun to learn and informative.